Hi, welcome back. In this lecture, I will further discuss collective communication and computation in MPI. So the question I have is how deterministics are collective computation. This also means if I do exactly the same collective computation, will I get always the same results? Well, in exact arithmetics, we always get the same results, right? But when we use a computer and we use finite precision, we do have round-off error and truncation error. So MPI does not require that the same input give always the same output every time. So, deterministic computation and reproducibility is not part of MPI. Of course, implementation are encouraged, but not required to provide exactly the same output given the same input, right? So round-off error may cause slightly difference, but also we look at the problem of associativity in the first module of this course, and we saw that we cannot really reproduce the exact summation unless we also enforce that the order is the same on the all operation. So the round-off error might cause slightly difference in the results. All the reduce does guarantee that the same value is received by all processes for each call. So it's guaranteed that we all have the same value, but it might not be the same value that has been produced from another run. Well, so why didn't MPI mandate determinism? Well, the major reason is because not all the application need it, right? So the only example I know that requires exact reproducibility of the results are the weather forecast application. So for instance, this is called IFS, and they implemented their own collective to enforce that the collective computation is reproducible. MPI provides a mean to define our own collective operation using basically one operation, that is MPI op create, by basically giving a pointer to a user function that we are going to use for the reduction. We also give a flag to say if this operation is commutative or not, and then we basically we give the name to our operation. After the usage of our operation, then we need to frame with the opening frame. So the function that we're going to use for the reduction need to be basically defined in this way. So this will be our user function. We provide the input vector, the output vector, the length, and the data type. So the user function should perform in the following way. So the output vector should output vector should be the input vector operation, the input output vector, right, from 0 to the length. So the user function can be non-commutative. So for instance, if we do like a matrix, usually defined on the matrix multiplication. Matrix multiplication is not commutative, so we need to say that is not commutative. So under the collective operation, also there are some collective operation related to the creation of groups and communicator. In particular, something that we are going to use and is quite useful is actually to split original communicator in another communicators and providing groups. So the way to do that is we use the MPI com split. So this is a collective operation over an input communicator. So in this case, we have old com. That is our input communicator. The partitioning group is based on colors. Other ranks in the new communicator are based on key. Usually the best routine for creating a new communicator over a proper subset of processes. So don't use MPI com create. There is also a new function in MPI 3 that is called MPI com create a group. So you get the all communicator, and here explicitly we have the communicator, integer for tag, and the new communicator. So this is new in MPI 3. It's collecting only over the input group, not only on the old com. So this is good news for performance. Requires formation of the group using MPI group creation routines. So we need to use MPI group to get initial group, and then we have additional function for handling the groups, like MPI group include, MPI group range include, MPI union, and so forth and so on. What is the collective communication semantics? Collective routines on the same communicator must be called in the same order on all the participating processes, right? So we cannot put a different point at our application. So we will need to be called always at the same point in our application. If multi-threaded processes are used, so for instance, we are going to use open MP within MPI, if the user responsibility to ensure that the collective routine follow the above rule, right? So we need to make sure that all the threads participating in collective communication, so part of a communicator, need to call the collective routines in the same order. So message tags are not used in the basic in the collective communication. So the way to differentiate between different messages having collecting only a particular subset of processes actually use different communicators to separate collective operation on the same process. Right, so we can use different communicators. So for instance, we can use MPI com split. As I mentioned, also there are non-blocking collective operation in MPI. This was being introduced in MPI 3. So all these non-blocking version, they return an MPI request, and they use the usual MPI wait, MPI test to complete. Might be mixed with a point-to-point and other MPI requests coming from non-blocking operation, and it follows exactly the same ordering rule as blocking operation. There is also MPI non-blocking barrier. That's quite interesting. You might be wondering why there is a need for having a non-blocking barrier. Well, it might be needed for if you are doing some distributed termination detection. A very interesting collective operation introduced also in MPI 3 are the so-called neighborhood collectives that are meant to basically to do exchange of ghost cell or a whole exchange in the PD solution, right? So if you have discretized equations, so there is also collective operation to do the swapping of whole exchange. So this is working for a Cartesian virtual topology, so MPI cart, and also only work for immediate neighbors in the coordinated direction. So if you have 2D, we work in the x direction and in the y direction. And also is available for graph topologies, but the support is not as high performance. A very interesting call is the MPI neighbor all-to-all that basically send distinct message to each neighbor. This means that in one call we have a whole exchange instead of coordinating all the message in one way or to the other one, right? So we can replace all the communication to the neighbor by just one call, that is MPI neighbor all-to-all. There's also the non-blocking version with I, so immediate MPI neighbor all-to-all for a non-blocking version. And the more important point that is MPI neighbor all-to-all provides a way to a very nice alternative to holo exchanges. So this was this last slides of this lecture. In the next lecture, I would like to introduce MPI one-sided communication mode and see which different function can take advantage of one-sided. Talk to you soon.